So now that we've gone through current carrying wires, we're going to move on to rings and solenoids that carry current as well. Right? So this is 5.2 magnetic fields. And again, if you haven't done the reading, please do so. It's in Untitled Chapters 21 and 22. Magnetism, Chapter 6 in the sapling homework in Physics 112. If you're in Physics 131, it'll be homework 8. Again, this is going to be labs 11 and 12 in 112 and 131. All right. So when we've seen this picture before, where you have a current carrying wire, and that current carrying wire, it's got a current going up or out of the page. I guess looking at this, I'm going to mark up this document. I'm going to hit the comments area, put it back, and then my drawing tool. So it looks like here you have a current out of the page, because that is going to create a counterclockwise directed magnetic field. Okay, so this current is out of the page. So I don't know which way this is working, but I'm going to just call it out of the page. I won't know unless I put a compass here. But you can see the iron filings, again, are making a circular pattern around a wire. Well, they're going to continue making a circular pattern around a wire, whether it's a ring or a series of rings, or what is called a solenoid, right? So let's see what we're working at right here. So we have a ring right here, and if you know if you look at it, the iron filings look like they're making little circles around each of the rings when it's coming in and out of the page, right? But it also looks like they're going horizontally in between at the center of the ring, okay? And according to the picture down here, it looks like this current is going to be a dot, because it's going to be out of the page, because these are going to be counterclockwise. So that means it's coming out of the page here, and then it's going into the page here. So I'm assuming that this is reflected upon this. That means this is coming out of the page towards us and then into the page here. So this current is in the page, and this is a dot out of the page, right? So that means this guy at the center is going to create a B field as just to the right, while this B field is going to be counterclockwise at the top of the ring, and the bottom ring is going to be clockwise. Okay? Well, this is going to be carried over here, right? What's kind of neat, though, is if you group up a series of rings, okay, in like a really, really long series, well, now look at this. This is actually starting to look just like a magnet, right? Where this would be the north side of a magnet, and this is going to be the south side of a magnet. So when you group up a series of rings, it actually starts to look exactly like a magnetic field caused by an actual magnet, right? Where the center of the magnet, you know, you'll have a magnetic field pointing just to the right. But isn't that kind of neat? So we're going to study specifically current loops and solenoids, because it's kind of hard to picture this, because it's actually kind of like two wires right next to each other, right? If you didn't care about this ring, ignored this ring, this is actually just two wires, a wire out of the page and another wire into the page, right? This is just a series of out wires, right? A bunch of wires out of the page, and a bunch of wires into the page over here. So if you grouped up a length of wires with currents pointing out of the page and the length of wires with currents pointing into the page, it would look exactly like this too. It's the fact that it's a ring, which is kind of a little bit weird. The tactics that we're going to use for a loop or a ring of current carrying wire is going to be the same that we're going to be doing just for a regular wire. You need to establish coordinate system. So X, positive X is to the right, positive Y is up, positive Z is out of the page. You're going to use the right-hand rule just like we did before, but you're going to use the right-hand rule on one part of the ring, which is going in or out of the page, and the same right hand you're going to use for the other ring out of the page, and then you're going to group up those curls where they take kind of a summative effect, where they add upon each other. All right? And so if you're having a hard time picturing the ring, so this ring right here is coming in and out of the page. It's out of the page and going into the page. It's hard to picture that. But imagine if you turned the ring on the side and cut it in half. Well, now that's a piece of paper. That's a plane. And that plane is going to now twist a little bit. It's going to twist a little bit here. And then now you could see it's actually coming out of the page here, and then that current is going into the page right here. So this is an X and this is a dot. Okay. And then when it then curls even more, well, now you can see it from the perspective of what it would appear to be right here. Okay. And so I want to show you this cool little if you're having a hard time picturing this, there's a cool little link that I put right here, and it sends you to right here. Okay, so this is kind of like a ring. This is going to be you can make two rings, right? Where they're both blue means the current is into the page, so negative current is into the page. Positive current is out of the page, so positive is the magnetic field is going to be counterclockwise. You can make it into the page, which will be clockwise, and you could change the other wires too. So now this is a ring, right? So this is going to be out of the page and then going into the page. And so you could see what would happen if you had two wires, or in this case, just a current carrying ring pointed out of the page here and then coming into the page over here, right? So this is a cool little link to help you kind of picture the magnetic fields in different perspectives for current carrying wires, for two current carrying wires, and also a ring, a current carrying ring. So I wanted to show you that before we moved on. Okay. Well, let's practice this, and we're going to practice the right-hand rule. Okay, the hardest part, I feel, if you're doing two wires, is actually doing the two wires, but with using the right-hand rule, and then going ahead and the quantification is not too hard. It's again, which we'll get into how to quantify this, but it's pretty simple. Let's practice the right-hand rule. So what I want you to do is you have a current carrying ring, and the current is going counterclockwise here. And I want you to apply the right-hand rule to find out the direction of the magnetic field here at the center at A. Also outside the loop to its left, outside the ring to its left at C, and also above it at B. So go ahead and apply the right-hand rule to those different points and see what you get. Well, let's go ahead and try it. So I'm going to imagine the direction of the magnetic field around the wire at the top here. Okay, I'll mark up the document here. So the current is going to the left. Okay, so I'm imagining a magnetic field that's going to make a ring around that top part of the current, which is to the left. So I'm pointing my thumb to the left. Okay, and it looks like it's going to be making out of the page at the bottom of the ring. So it looks like the B field, when I'm curling my fingers, I'm curling my hand, keeping my thumb pointing to the left of my screen, curling my fingers, and my fingers, when I curl them down, they're pointing at my own face. At the top of the ring, keeping my thumb, so up here where B is, up here where point B is, above the ring, keeping my thumb pointed, my fingers are making kind of a claw in front while my thumb is pointed to the left. And that looks like the B field is going to be pointed into the page. Right there. Interesting. Well, I'm going to follow the current along the ring, and the current is going to be traveling straight down here. It's again going to be making a ring around there. And again, I'm getting dots. I'm getting my fingers when I keep my thumb pointed down the page, so my thumb is pointing down the screen. My fingers, when I curl them around, again, looks like the B field is going to be out of the page over here, close to this wire. And it looks like it's going to be into the page over here at point C. Right? My thumb is pointed down, my fingers are pointed into the page, kind of making a claw. I'm going to continue trying this. Here I have a current pointed to the right, so my thumb is pointing to the right of the screen. And when I'm holding my hand, I'm looking at my own palm with my fingers curling towards my own face. So again, I'm getting dots, again, pointed to my own face. And again, below this wire, I'm getting a B field into the page there. And what you find out by doing this is that all over the place, anywhere you go outside the ring, you're going to have a B field into the page for this counterclockwise current going around this ring, and it's going to be a B field out of the page towards your face at the center of the ring, just by applying the right-hand rule. Okay, so that's how you apply a right-hand rule to a ring. You've got to continuously keep your thumb pointed in the direction that the current is moving as the current is going around different points. Okay. Well, now that we know how to apply the right-hand rule to a current-carrying ring, how do you calculate it? Well, turns out a current-carrying ring takes on this form. It's a magnetic field, which is which is equal to mu I, and it's I is it for a current-carrying ring over 2R. Right? If you have multiple rings, you're going to multiply this by the number of rings. So if the number of rings is 1, well, that n is just going to be equal to 1. If you have multiple rings, well, you're going to have a whole bunch of those n's. Well, now you're going to multiply it by 3. Okay? If there's 3 rings, 3 full loops, there would be that number n would be 3. And again, mu naught is a permittivity of free space. It's 4 pi times 10 to the negative 7th Tesla meters divided by amps. Okay, so that's how you calculate this. So again, you can't just get a magical ring. I want to point this out, that even though we write this like this with a current going around in a loop, okay, you can't really get that. What you basically have is you have a current sending, you're being a current sending along a straight wire, and then you just create a little loop around something, and then after it completes that loop, it's going to then continue on in the wire. So you're imagining the magnetic fields around a straight wire, but it just happens to make a loop. So whatever the magnetic field is around the straight wire, it's going to continue that kind of that circular pattern in and out of the page, but directed towards the center of the ring. Okay. There's a special case with a solenoid. Okay. With solenoids, and they're a bunch of rings, just like we've seen before, but with a solenoid, they could actually have so many wrappings of rings, okay, that in fact the radius stops mattering. This radius becomes inconsequential because right here this is a really small radius. Well, if this length of wire goes on for infinity, the length is a huge length, right? Well, this is going to, if we zoom out, this solenoid is going to look like a straight column of rings going on forever and ever and ever. And you're actually not even be able to see the radius of that. So at some point, even though we've talked about solenoids, the radius won't even matter. So when you're calculating the magnetic field inside of a solenoid, all right, the radius is actually going to become inconsequential because the length is going to be so big. It's going to be so big that the radius is going to be the radius is going to become unimportant. So it's kind of weird. What you find out is that it's mu naught I, but not over 2r or 2 pi r. It's just n over L. And this is actually kind of like the density of the number of wrappings per length. And that should be an L. So this lowercase n is actually like the density of wrappings per the length. Okay? So if you're asked any questions, like in the quiz, you increase the radius of a solenoid by 2. If you increase this radius of the solenoid by 2, what is going to happen to the magnetic field? Well, nothing. The magnetic field is going to stay the same because the solenoid is dependent upon the length, not on the radius of the ring. Okay? So what I want to do is, it's always good to keep practicing. So we're going to keep practicing what we've done earlier. And this is related to the rings. If you imagine this is actually just a ring out of the page and going into the page. We're still practicing rings and small solenoids, or multiple rings, but not solenoid stuff. But we're doing it with wires. But this is a cool game that Mark Summers created. And so what you're supposed to do is figure out the direction of the current in the question mark wire. If you know the current of the other two wires, so basically if you add up the magnetic fields at this point A, it should add up to be equal to 0. So the B field here is supposed to add up to be 0. Well, you have a wire I. Wire number 3 is a current just 1I to the top of the page. This wire number 2 is current 1I down the page. What does this current have to be in order to add this up to be 0? Okay, so let's go ahead and do this one together, and then I want you to try this other one, which is in a different dimension. So let's go ahead and apply the right-hand rule. And I'm going to remove my writing. I'm going to use some colors to do this. So we're going to associate blue with this current. And we're going to associate red with this 2I guy. And we're going to associate green with this 1I guy, right? And I should, so anyways, let's go ahead and calculate it. Well, let's figure out the magnetic field around the current carrying wire due to the blue wire. Well, this is a blue wire, so this blue wire is going to be creating, I have my thumb pointed up the screen and my fingers, so I'm looking at my palm, my thumb is pointing up the screen, and I see my fingers are pointed at my own face. So the blue wire is going to make an inward pointed magnetic field. Okay? And in is negative z. So I should probably have written my coordinate system here off to the side. So I'll do that now. That positive y is up, negative y is down, positive x is to the right, negative x is to the left. Into the wire is negative z, which is in. Positive z is out. Okay? I'll put a little markings on that. So the blue wire has a magnetic field pointed into the page, right? So what does that do? Well, that means it's pointed in the negative z direction. So that blue wire is a negative z. Well, let's try the magnetic field due to the red wire. The red wire, I'm going to point my thumb to the bottom of the page, and I'm curling my fingers down, and it's really kind of hurting. I should work on my mobility for my wrist. While my thumb is pointed down, and I'm looking kind of at my palm, and my fingers are pointed out of the page. Okay? So, right here, so this, so the red wire is going to create a positive magnetic field out of the page. Okay? Right. Well, how do we figure out the direction? So that means this has to add up to be 0, right? So we need to figure out the total magnetic field. The total magnetic field at point A needs to be equal to 0. Well, that's going to be equal to the magnetic field due to the number 2 wire, which is out of the page, plus the magnetic field due to the number 3 wire, which is into the page. So that's why I'm writing it negative. And I'm going to go plus whatever the magnetic field due to the green wire is. Okay? And that has to add to be 0. So all of this has to add up to be 0. Okay. Well, this is 1I, and this is 1I. So the B field due to the number 2 wire is going to be plus, and that's going to be mu naught, and that's 1I, and it's 1d away, so it's going to be 2 pi, and it's 1d away, plus the B3 wire, which is, actually that should be minus, plus the B3 wire, which is also a 1 current wire, and it is also 1d away, 2 pi, and that's 1d away, plus our B1 wire, and that's got to be equal to 0. Well, actually what you find out is that these two guys already cancel themselves out, right? This is equal to this, and since they're subtracting, so there can't be a current in the B1 wire in order for this to be equal to 0 at the center. So that's what you're trying to do. You're trying to work out the mathematics, the current, the amount of current, and the direction of that current, so that the magnetic field is going to be 0 at that point, considering the other wires. Right. Well, what I want you to do is I want you to try what we just did, but you're going to try it for this. You have a 3I wire with a current pointing out of the page that is 1d away from point A. And again, you need to make sure that the magnetic field at point A is equal to 0. So the 3I wire is going to be has a current out of the page. The 10I wire has a current pointed into the page, and it's 2 Ds away. Well, what current does this have to be in order to make sure that that B field is 0? So I want you to try that. Okay? Pause the screen now. Well, let's go ahead and do it. This 3I wire is going to be, I'm pointing my thumb at my own face. It's going to be creating a magnetic field to the left in the negative X direction. The 10I wire, I'm now pointing my thumb into the screen and curling my fingers, it looks like clockwise. The 10I wire is going to be creating a magnetic field that is to the right, and it's going to be 10I. I don't know what the direction of this number 3 wire is. Since I don't know, I'm just going to assume it's also pointed to the right. And that way when I add this up, I can set it equal to 0, and it makes it pretty easy. So we're going to do this, the mathematics down here. So the total B field at A, again, needs to be equal to 0. And that's going to be equal to the negative, the 3I wire's magnetic field plus the 10I wire's magnetic field plus the B3 wire, and that has to be 0. Okay, so 0 is going to be equal to this. So then the 3I wire is going to be mu naught 3I, and it's a distance 2 pi d away, plus its absolute value, plus the 10I wire, and that's 10I over 2 pi, and it's 2 Ds away, plus the B3 wire. And so the B3 wire, we're just gonna call it B3 for right now. Okay, and that's got to be 0. So working this out, I'm going to bring these guys onto the other side. So I'm going to work this out to a number. So that's 3I. So this is going to be 10 divided by 2. So this is going to be 5. And this is going to be 3. So this is going to be equal to mu naught I over 2 pi d. And this is going to be 3 over d. So this is going to be equal to negative 3 plus, and this is 10 divided by 2, so that would be 5 plus B3. So this is going to be equal to 2 mu naught I over 2 pi d plus B3. So what that means is, I'm running out of room, that B3 is going to be equal to 2 mu naught I over 2 pi d. So I'm going to keep the 2 pi d there. I'm going to bring that onto the other side. So that's going to be equal to negative mu naught, negative 2 mu naught I over 2 pi d, which means this B3 is going to be equal to a negative 2I. So, is going to be analogous, is going to be due to a negative 2. And X is into the page. Okay, so when this, what this means is this B3 is going to be pointed to the left. I was wrong in my guess. That green wire, actually that B3 wire is not pointed to the right. It's going to be pointed to the left. And that is going to be a 2I wire pointed to the left. Right? So this this B3 guy is due to a 2I wire. I got that -2, and I is going to be mu naught I over 2 pi d. So basically this is -2 mu naught I over 2 pi d is the issue. So that's got to be pointed to the left. And that means this has got to be a dot, and it's got to be a 2I wire. So this is a 2I wire, and it's a dot. So this is a 2I wire out of the page. So you have some lecture tutorials that are just like this. So what I want you to do is go ahead and practice this and go ahead and go try those. Thank you very much for watching.